Hello fellow engineers and welcome back to Hydrology Engineer. Now this is the game that isn't really a game, it's actually an advanced engineering tool, but they've added graphics to it to make it sort of like a learning thing. It's a hydrology engineering learning resource simulator. Now I've already done 2 videos on this which you guys seem to love despite it being me literally just doing my old day job, which I quit to do YouTube. But remember there's more levels, so let's have a look. Let's go on to level 2 this time with added utilities. Now utilities are they're basically like the services like pipes, cables, internet wires, all that sort of stuff. So I'm guessing for this one, when we design our pipe network, we're going to have to dodge out the way of those. But let's get into it and have a little look. So this is our new map. Oh, which I say new, it is actually the same. I think it's the same layout as previously. But yeah, we now have surfaces to deal with. We've also been told we also need to drain the roofs. So these roofs have can you see the down pipes? So basically all the water that lands on there, it's got to go somewhere. And if you have a look down at the bottom, can you see down here the down pipe? That just goes onto this grass, which means this grass, which I believe falls towards our road, is going to have way more water contributing towards it, which means we're probably going to need way more gullies than we had previously. Now, 2 things before we start this. It's worth noting that in real life, you wouldn't build the road and then come back and build the drainage. Whilst this does look realistic, it's not meant to be real. It is still meant to be a computer sort of visualization before we actually go to site and build all this stuff, because generally the drainage actually gets built first. That's because the drainage is under the ground, so you lay your pipes first and then you come back and put your road on top, so that your road, when it does rain, it's got somewhere to drain to. So whilst it's the thing that you design last, because obviously you need to know what's contributing towards your drainage in terms of hard areas, soft areas, that sort of stuff, it's the first thing that gets built. So no pressure on us drainage engineers. Anyway, if I was sat at my desk in my old job, I'd probably be given something like this from the designers, and it would come with contours. So boosh, let's just turn those on. So basically it's a 3D surface and the contours show us quite easily which way the road is falling. So you can see we've got a high point up this way, we've got a low point over there, we got another low point there, and obviously after a decade of drainage experience, I have learnt firsthand water flows downhill, which you might think is obvious, but it's incredible how much drainage is actually put at high points and not low points. And therefore you get puddles everywhere. Right, the other thing worth noting is if we just head under the ground, look at this. Whoop. Oh, we're under the ground. You can see these are the utilities we were warned about. And as I said before, utilities are basically the services that go to pretty much everywhere. So we've probably got gas, we've probably got sewage pipes, probably got water mains, telephone wires, normal wires, internet. And in most cases, that stuff is probably already there. So we need to work our drainage around it. You do get the odd occasion, say you are actually building a brand new housing estate like this, where you may build all of that stuff at once. And then you generally get quite a nice little setup where basically in the road, they say, right, the first meter on the left, that's reserved for drainage. The next meter is reserved for telephone wires, then gas, so basically everything's segmented and then you don't get any clashes. But most of the time it doesn't work like that because we're sort of working with things that have been there for years and years. So it's all about trying to make your drainage flow downhill whilst dodging all of these services. Now it's worth noting we have been told that the higher ones, these are the water mains. So basically all of these houses, to get water to your taps, you have high pressure water mains. So basically water is pumped through pipes at high pressure so that when you twist the tap, water pours out of it in your house. So they're at the highest level on this. You can see down at the bottom here, these are the sewage pipes, the waste. So basically when in your house, say you flush the toilet, say you run your tap or whatever, all the water that goes down the toilet, it all goes somewhere, and that somewhere is down at the very bottom into your wastewater sewers, which then end up hopefully not in rivers. Hopefully it goes via some sort of wastewater treatment first. But yeah, so that ends up somewhere else because we're worried about the surface water drainage, the drainage from the rain in the sky. And so when you look at these, you want to make sure that your pipes are always above these wastewater pipes, because if you remember, our surface water generally ends up over in a pond where it evaporates or soaks into the ground. And so if our pipes were below the foul sewer, and this sewer then leaked, all that poo water, the horrible sewage, would leak into our drainage system, and then that would end up over in our pond, which obviously wouldn't be very nice. This area would be full of poo. It would look like Endertopia or something, and we don't want that. So generally, a hard and fast rule is that you always put your surface water drainage above the foul sewer. It's also worth noticing as well, can you see like where this connects? So there's a bit of a junction there. There's 3 foul sewers coming together. You would usually have a manhole there, and say we were designing like this whole estate at the same time, we'd try and put the foul manholes and our surface water manholes, you'd put them as close together as possible. So remember, a manhole is this. It just allows you to like access pipes. But generally you'd have these like rather than having like the surface water one over here, the foul one there, you'd have them as close together as possible. That's because when we build it, we can dig just like a really large hole and then put both these chambers in. And as long as your surface water one is shallower than the foul one, then you've basically saved like a lot of digging money, because you've only had to dig one slightly bigger hole than like 2 separate holes if your manholes were further apart. However, in this example, the foul sewer is already there. It doesn't even show manholes, so we won't actually worry about that in the slightest. So boosh, let's delete that. And then let's start with doing some actual drainage. So to start with, before we can worry about pipes or anything, that rain falls onto our surface, and then we've got to get that into the pipes. So we will start by adding some of these gratings, which in the UK we call gullies, and this is generally what we'd use just to take water off a road. There's other types, so you've got like these ones which have like a little curb inlet on the side. These ones which are literally just a curb inlet. We don't use any of these in the UK really. You may see them like some places, maybe a bit more like rural areas, but the sort of standard for the UK are these gratings here. And basically to do this step in real life, it's sort of separate from the pipe network. So we'd just have like an Excel spreadsheet. We'd type in like all the sort of details of the road. So we'd have the falls, we'd have the contributing widths, contributing areas from the sides, etc. The type of grating and stuff. And basically, as you go like from your high point, which as you can see from the contours, that's the high point. So this road is falling this direction over here. It would basically tell you where to sort of space your gullies based on something called the flow width. So if we just run a storm, so this button up here says run storm event, and basically this puts this like simulates rainwater, and then you can sort of see like how your gullies work. So if we just do that, you should see, yep, the rain comes over, and then you can sort of see the water on the edge of the map here. Basically, the aim is to not have that water go too far like into the road. Generally in the UK, it's about 1.2 meters like flow width you're allowed. So from this curb into the road, the water can go 1.2 meters, and this is simulating like the worst storm possible. So I think when we do gullies, is it a 1 in 30 year storm or a 1 in 5 year storm? Basically the worst storm that's likely to appear once every 30 years or once every 5 years. I literally can't remember. It's been quite a few years since I've done actual drainage, and of course the standards change all the time, so my knowledge may be slightly out of date. Thankfully though, in this game they give us their own rules, because quite often these can be set by like individual councils. Particularly I think this is like US based, so US is going to be a lot different to the UK, and they also call it gutter spread rather than flow width. So you can see down here theirs is 2.4 meters that this water can go into the road. So that basically means these gullies are way too close together, because if we get our measuring tool here, look, we can see exactly how wide that gutter spread, that flow width is. So we can add another 2 meters on. So basically I can take this gully and probably move it like all the way down there, and this first one, move that down to like, I don't know, over there-ish. And then if we run the storm again, that's the thing with this game, it's sort of more trial and error than real life. In real life, you do like all the calcs to work out like the flow width as it goes on, and then it will just like tell you like where the 2.4 appears. So what is that? Oh, that's still only a meter. Blooming out. Okay, then I'm literally wondering, if I were to put this at the low point, which is down there, what would the flow width do on this side? Let's run one more time. So, oh boy. I guess that's not too surprising, because it's important to note when you're working with low points, you can't just look up one side of the road. It's a low point, so there's going to be another side of the road that's also contributing to your side. We've also got this side of the road as well, which like probably isn't helping. So let's just get my measurement tool out. So it gets to there 1.5 meters, and then it just goes mental, like there's so much water down here. Over this side it gets to about 2 meters wide. So what I'm thinking, let's just add another one to the low point down there. I can probably actually work around like all of these. So we can see like the flow widths like coming from this end, because up here is a high point as well. So if we just measure along here, when we get to 2.4 meters, which is after that driveway, so we can tell roughly where we want to put a gully on this side. Now, because that is a driveway, there's no curb upstand. A curb upstand being like this vertical face of a curb. You can see it's a dropped curb there so that people can get like to their drives. So we can't actually put a gully there because it won't work as well. Most of the water will like go around the gully. So you always want a vertical upstand. So I reckon let's just put that one just upstream like that. So then all of this water here, this massive flow width, it should reduce down quite significantly into here. Granted, some of it will still flow past. Hence, you'll often find if you have like a straight road with completely even width slopes and everything, you'll notice your first gully is probably got a larger spacing than the ones like downstream. That's literally because some water will flow past. But yeah, for this, trying to work out the actual spacings is going to be quite difficult, because not only do we have all of this grass contributing, we've got these driveways which are hard. We've now got all of these roofs and all of these downspouts. So I think for now I'll just trial and error them. Over this side though, we can go find 2.4 meters. So look, it's all the way around here. So it gets to like 1.8 and then it actually reduces. I assume that's because that goes a little bit steeper, so the water like flows a bit faster. But yeah, okay, we'll shove a gully at the low points on that side. We can probably look at this side. Yeah, 2.4 is around there somewhere. So we'll shove a gully about there. I don't actually know what that's meant to be representing. Is it like the amount of water coming off like the side? Because like looking over here, I can see there's quite a lot of downpipes from the roofs. There's also quite a large grassy area. So maybe that's what that's meant to represent. Anyway, we'll shove gullies at the low points. So one there, one over this point. All right, then we'll run the storm event again. All right, and I think first we'll head up here. So this is where I said some water will bypass your gully still. So you can see their flow width gets up to like 2.25, and then a lot of it enters the gully, but some will go past. So it means down here we get to 2.4 quite quickly. And again, it looks like it happens at a driveway. So we'll shove our next gully just upstream of the driveway, and then we can start looking at the other side. So again, we know round this corner stays under 2.4, and then it goes to 2.4 about down there. So just shove a little gully there. Okay, you might be wondering, well, Matt, that's so close to the low point. Obviously, between the two, it's going to be a really low flow width. So surely I should move this gully like up. No, you should always work from upstream, mostly because low points are the most important part of a drainage network. Obviously, if this gets blocked or whatever, then, and you can see you get a massive puddle across the entire road. That's completely flooded. Road gets blocked. So by doing your spacing from upstream, it means that less water is going to go into this gully, which just means it has like extra capacity should something go wrong upstream. All right, so we'll head over this way and do similar. So that's the gully we put in. This goes to 2.4 about there-ish. Add another gully there. Opposite the road, that's actually, is that sort of okay? It goes to 2.41. Let's just have a look in the rules. Yeah, it's actually 2.43. I think these have all been converted from like the crazy imperial system that Americans use into the proper metric system. So the values are slightly odd, but it does mean that gully is actually okay in terms of spread. By the way, just ignore the fact that Brits put mile an hour on signs. Most other things are metric. So coming from this way, it does look like we're going to need one gully just to reduce the massive amount of puddling down there. I mean, generally, we would actually put two gullies. Like, there'd be one gully pot, like the concrete bit under the ground, but you would have two inlets at the very low points, basically just to account for what I said before, like the uphill being from that side and also from that side. But in this game, I don't think you can do that. I mean, what I could probably do, I could replace it with one of these curb inlet things. They're probably way better at a low point, because they take like more water. So yeah, I think I can select this. I can say, let's change it to a B5 combo box. So that will probably take more water. Actually, if we just have a look at this, and I'll do the one on the opposite side as well. So that's also a combo box. So if we run the storm again, will there be less flooded water there? So editor, show the before and then flash to the current of this one. You can see, yes, there is actually way less water. Sort of. I feel like this side of the road is fine now. This side, though, is still a little bit sketch. I think that's mostly because we haven't finished doing our drainage up here. So we put that gully in last time. We go find where 2.4 is. Is it going to happen? It's going to happen at a driveway again. So wang another gully there. Run the storm again to see how that worked. So yeah, that stretch is all below 2.4. Then down here, yeah, you can see it gets to 2.4 before we get to our combo gully at the bottom. So let's shove that in like there. Run it one more time. Do a cheeky bit of measuring there. So that stretch is all good. Down here does still go too wide. So I think we need another gully on that side of the road. I think 2.4 appeared about there-ish. So now with gullies either side of that. Oh no, it's still not good. That goes up to 2. Blooming out. Okay, so I think this is flooding because we got such a large amount of water contributing it behind. Can you see like this sloped bank? So most of the water that lands on this grass will be flying towards our road. We've also got this quite long driveway. We know that we've now got all these downpipes, so we've probably got all of that roof contributing. So what it may be worth doing is just shoving another gully sort of up there just to take like most of this water, because basically all of that area is all contributing towards this gully. Whereas if we sort of reduce that down a bit, then these gullies should only have to worry about like what we've got right next to it. So run it one more time. You can see this gully we just put in is taking quite a lot of water. There's still quite a lot contributing down here. Yeah, it's close. It goes up to 2.5. Now, because there's quite a flow width that's getting past that gully, in this game, the obvious thing to do would be just to upgrade it with like one of these curb inlets, because they probably work better. But since I want to do this the British way and we only use these gratings, I think what I probably would do is just shove like another gully a bit further upstream. Let's say like there. So that this is taking most of the water. Whatever flows past that goes into this one, plus like this little strip, which should mean overall less water makes it down to our low point. And just in case you're wondering, no, I can't actually fit in like another gully between those, but otherwise that's what I'd do. And those with a keen eye may actually have noticed, like in the real world, you may have seen like gullies. Generally they're spaced like fairly infrequently, like they're quite far apart, but then you may see like a little area where it's sort of like this, where there's like loads of gullies close to each other. And that's pretty much how you can spot like where there's probably a low spot. And rather than just a low spot, it might just be that it's like a flat spot. So obviously as your road gets like flatter rather than steeper, you're going to need more gullies because the water isn't going to be flowing as fast. And it's worth noting in the UK, we actually have a sort of like a minimum sort of spacing. So once these gullies get to like less than a 5-meter spacing required, we often swap to a linear curb drainage system. Now these look like this. So they're basically curbs that are hollow and they have holes in the side of them. So it just allows the water to inlet like all the way along the curb line. You don't have to wait for like a gully grating to appear. Now these are really good for flat spots because obviously all the water that touches the curb just goes straight off the road, rather than like a gully that we've got here. As the water touches the curb, it's got to flow along the curb until we get to a grating. So that's the benefit. The reason why a lot of people don't like using them is they're quite hard to maintain. Like if you get like a leaf block up one of those holes, then your curb inlet isn't going to do anything. And the actual maintenance of trying to clear a curb line is quite a lot more difficult than just like trying to clear one of these gratings, because the gratings generally you can just like scrape off the top, sometimes remove the grating, get like a gully sucker in there just to get rid of all the sediment and stuff. But when it's like in a curb, like a tiny little hollow structure, it's really difficult and time consuming to like clear those. But if you've ever wondered what the curbs with holes on the side of the road do, now you know. Anyway, I've run this storm again. You can now see this gully here, hardly any water's flowing past it. And if we now measure at our low point, you can see we are below that flow width of 2.4. We're down to 2.3. So I think this network is good, right? I think for consistency, I will just upgrade all of these low point ones to the combo box, just to show that it is a low point. In the UK, this is where the double gullies would be. Oh yeah, there's a low point up here that I completely missed. So shove that down there. Make sure it's this B5 combo box. Check all the widths are below 2.4. Nice. So that is our entire network drained in terms of we've got the gully spacings down. And you might notice this from last time, because I've actually followed the rules of the game rather than the British standards, way less gullies. So it should mean the pipe network is significantly easier to build, although this time, remember, we've got to dodge those underground utilities. So if we want to build our pipe network, basically we always need to have a manhole between every pipe. So we start off with a manhole. We've got our gully up this way. We can see the road flows downhill over there, so that's quite nice. The thing I don't like is the high point is actually there. So whatever we do over this way, the pipe coming out of there is going to be flowing against the gradient of the road, which means it's going to be getting deeper and deeper, which isn't great. The thing that's worth noting though is these gully pots, like they're generally quite a lot shallower than these manholes. And these manholes, because they're going to be in the road, they're generally going to be about 1.2 meter depth, because at that depth you can have cars drive on top of your pipes without worrying about them getting crushed. If they were shallower than that, then the pressure of the cars driving on top, it would actually crush your pipes. And then that depth, it actually changes if you were to put your pipes just through a field or something, because you're not going to get cars driving over a field. So generally you can go down to about, I think it was 600 mil cover in a field if there's not going to be any traffic on it. 1.2 meters depth in a road, and that's to the top of the pipe, like the cover of the pipe. Also worth noticing, we generally go 30 meters from a gully to a manhole. That just allows us to clean from the gully to the manhole quite easily. If it's longer than that, it gets quite tricky. And then the distance between manhole to manhole, you can usually do 100 meters. I think in here it's slightly lower. Yeah, max pipe length 91 meters. They don't actually seem to have a max gully tail length, so that's a pipe coming out of the gully. They don't have that 30 meters, so technically I could go from this gully 90 meters away down here. So what if we were to actually try that? So if I put that in, could I then grab a pipe? The smallest I can go is a 300 mil diameter. Generally for a gully tail, you'd actually do 150 mil. But yeah, we can connect from that gully over to there, and you see it's 45 meters long. So we'll put that in, and then you can see, oh look, we have an error warning. That is because if we head under the ground, we are too close to this water main. So yes, we are below it, but we're a bit too close. You generally want a bit of clearance just so you don't interfere with it, because these pipes, they're generally laid with a surround of gravel or some sort of granular material. So basically, if that's touching this water main, that's probably a bad thing. So two things we can do. We can either make one of these deeper, so probably making our manhole deeper would be sensible, or we could just move our manhole upstream a bit. Making things deeper is very expensive usually. The depth here is the minimum, so let's just see if we were to move this upstream, let's say over to there. Oh look, no, we're still clashing. So in here they're saying we've got to be 0.457 meters below the mains water. We're 0.422. Oh, we're quite close actually. So I could just make this manhole a tiny bit deeper. Alternatively, may as well just move it up there a bit. So yeah, now that pipe is below the water mains. You can see it's above the sewage pipe as well, so that's perfect. Does mean we now need a pipe up here for this gully. So manhole there. We can then connect from this pipe down to that manhole, and then from this gully to that manhole. So now you can see our pipe network goes completely parallel with the road. You can see it going downhill. And it looks like our mains water is actually, it's under the verge. Can you see it's under this bit of grass? It's not actually under the road. So by putting ours in the road, we're well out the way of that. So that's pretty good. We'll shove another manhole so that gully can connect. Now it's worth noting, we wouldn't always connect these gullies to a manhole. We would be able to connect them to a pipe. So out of this gully, rather than connecting to this manhole, we would just branch onto the pipe, because you would still be able to access it to clean from this gully. It's not actually best practice though. Best practice is to do what we're doing here, but obviously this is really making the cost add up, because what do these manholes cost? Yeah, 4 grand each. They're pretty pricey. Anyway, from this manhole we'd probably have another one by that gully, and then another one down here. Now this is the low point, so it's going to be quite messy probably, so we'll add that in. And then if I just look underground, yeah, there's a water main through the middle there. So our manhole does miss that, so that's fine. But getting a pipe to go over this direction, we're going to have to be probably a little bit deeper than we currently are. So something to consider. But yeah, I think let's take a manhole, shove it there. You see down there the warning has appeared, but we will be adjusting the levels, don't worry. Then we'll take this manhole, we'll go between these two houses. Now generally, remember, we're doing this in a design period. So these houses aren't actually owned by anyone. anyone yet, so we can pretty much put our pipes wherever we want. It's just worth noting that there will be like a license required. So say you go through one of these people's gardens, their house, when they buy it, there'll be like a license so that whoever maintains this pipe, they have permission to come onto these people's land to like dig up the pipe and replace it if they need to. So you would probably try and limit how many gardens you go through, etc. But yeah, let's go to like, I don't know, there, and then we'll take that down to the pond. This goes out into a head wall. And actually, we'd probably go to a manhole first, and then a head wall like there-ish. And I always forget like how small they are.
That's what she said.
They look so massive on here. I think that's because, changing this pipe diameter, does that make the head wall bigger? Yes. Okay, that makes sense. All right, so you might be wondering, well, Matt, why did you put a manhole there? It's so I could angle this head wall so that rather than the water entering this place at a corner, it enters on this edge, so it has this nice long length of pond, because the water as it comes out there is probably going to be going reasonably fast, because this is quite a lot lower than like up where those houses are. And whilst we try and limit the flow velocity, like we've got like rocks here, you may sometimes see we put like little like concrete blocks like just on this sort of surface to slow the water down as well. But generally in like the worst storms where there's the most amount of water, you want to try and have like quite a long distance ahead, just so as the water enters here, it sort of slows down so that by the time it reaches like this wall up here, it's going so slow that it's not actually going to like erode it or do any damage. If we came in like at the corner like I showed, or even on this side facing that way, the water probably going to shoot out and start eroding this wall. And obviously if you start eroding your pond, you're gonna cause issues. Not only will there be like sediment and everything in the pond, you could flood somewhere downstream, etc. So generally just a good practice thing to do. It gives you the longest length as well. And then we'd also, should this just be like a storage pond, we have an outlet from it, we'd put the outlet down this end so that all the water, it has to travel along the entire length of the pond. That allows like sediments to settle, it allows like a bit of evaporation to happen. The grass in here should clean the water a little bit as well. And obviously the longer length you have, the more of that good stuff that can happen to that water. It gets it nice and clean before it goes into like a river or something. It looks like this pond though, it doesn't go anywhere. It just soaks into the ground. So this would be what we call an infiltration basin, because basically the water will infiltrate into the ground. That's compared to what we call a detention basin or a retention pond, where basically they just store water to allow us to limit how much comes out. And if you want to get into details, the difference between a detention basin and a retention pond is a detention basin is usually like dry most of the year, but when it rains it fills up with water. A retention pond is usually like wet the whole year round. They all have like different benefits and stuff. This one, because it's an infiltration basin, it's probably more likely to be like a detention basin, so it will be dry most of the time apart from when it rains, because remember the water's meant to infiltrate into the ground, so you want this to be dry unless it's just rained, really. All right, so anyway, down here we haven't actually connected up our gullies yet, so we'll just connect all of those pipes in. This pipe I'm going to go over to that manhole rather than that one, just because the angle, you generally want to keep it like 90 degrees so water's always flowing like towards the outlet. These gullies I can connect straight down to there, but yes, as you can see, they are clashing with the pipe. They're not technically clashing. Like if you look down that pipe, excuse all the numbers up there, absolute carnage. They're not technically clashing, but they're way too close. In fact, something we'd probably do here is what we call a daisy chain. So rather than this gully going straight into this manhole, we'd probably delete that pipe there. Boosh. So the water that enters this gully goes along this pipe to that gully and then flows to that manhole. It means there's only one pipe we need to worry about clashing under there. And also remember, this is only there because there's the flow was like sort of affecting downstream, wasn't it? So there's not actually that much area contributing to this one. So we're probably good to do that there. Worth noting though, this isn't best practice. Generally, daisy chaining is like quite a lazy thing to do, but it does save you adding like extra manholes and stuff occasionally. So some clients like it, some hate it. But yeah, for now we got to try and work out, can we get the clearance we need here, or will we actually need like another manhole maybe there? Because trying to get gullies to go deeper, we can't actually make the gully pot that much deeper. They're pretty standard. We can make manholes deeper. So rather than these gullies going across there and us trying to make this manhole deeper so that these are like steeper, it may be worth instead just adding like an extra manhole and then connecting all these gullies to that. I don't know. For now, let's let's try and make this a bit deeper. It's already 1.5 meters deep. The max depth we can go to is 4.5. So it's worth noting that isn't going to be the deepest one. Can you see the ground like goes uphill here? You can see it like along that way a bit easier. So up here, this is going to be quite a deep manhole already. This is probably going to be our deepest one. So yeah, it's already 2.27. If I add another meter onto that, you can see we've got the step there. So I want to lower that pipe by 2 meters as well. So if I just make that elevation a 1, then nice. That's much deeper. Although actually, I think that's deep. Yeah, that's deeper than the pond. So we have to bring this up a little bit. Let's bring it up by, I don't know, 500 mil. If we make that a 3 and that a 4, then that should be good. It means the upstream manhole here, we can now lower this because that pipe's really, really steep. So if we lower that by, I mean, we could do a meter. So yeah, you can see I'm just lowering all the pipes coming into it by a meter. So rather than a 3 there, that's the invert level, by the way. So generally, that's the height above sea level. And you can see we've actually have coordinates for everything down here. We've got X and Y, which are like the grid layouts, and then Z, which is always the elevation. And that always measures above sea level, usually, unless you got some sort of datum. Worth noting, actually, I found out on the last episode through comments, apparently some software and Minecraft, I can't believe Minecraft does this, but they don't have Z as their like height elevation. I think theirs is Y. And it's X and Z, which are like the like coordinates. That's a very much video game thing to do. In real life, X and Y are always like, say you're looking down, they're like your grid reference. So like your XY coordinates are always like actual location on the earth. And then Z is always your height. But yeah, not in Minecraft, which is crazy. So a generation of kids have been taught completely wrong in terms of like the real life. But yeah, anyway, so I've lowered those pipes. So we're no longer clashing with that. So that's good. You can see we're above the sewage pipe as well. So all we got to do now is connect these guys up. Better have a look to see where the pipes are here. Oh, ooh, that's a bit naughty. Yeah, because the water main's sort of in the middle of the road / this side of the road. I think I might shove manhole there. Next one there in the verge. And the next one connecting down over to that. Yeah, I'm going to be lazy and just daisy chain those two into there. I might even daisy chain these ones. They're all flowing downhill, so it's fine to do that. Yeah, that is actually something worth noting. When you do daisy chain, you can't do it like against the grade. So if you look at like the surface levels, can you see they're falling from this way down to the left? So our pipe is also doing the same. Oh, actually, that I don't know why that shouldn't be up in the air. But yeah, generally this pipe will follow like the gradient of the surface. So you can only daisy chain if you're going downhill. Thankfully for all this, that works perfectly. But we do have this here. So it looks like it needs to come down like only by 50 mil to be fair. So basically this chamber, I can just lower it by 50 mil. So if I just on the depth, turn that to a 6. That's lowered down. Everything is still flowing downhill. Nice. So I think that works perfectly. Although worth noting down here, that is quite a steep pipe. Minus 3.64%. So that is caning it down to here. So maybe worth trying to raise that. If I raise it by a meter. Yeah, I've raised that to a 2% slope. So that's like 1 in 50, which is way better. It means this manhole is now, oh, it's still 4.3 meters deep. Wow, how deep was it? I think it was way too deep before. I mean, to be fair, I should probably try and raise this manhole. Like, these are way too deep. I was just being lazy. I was doing it all to like the nearest meter. If I raise this up by half a meter, then yeah, that's much more sensible. And then this manhole downstream of that, I can raise that by, hang on, what level is that coming in? So we just copy that level, we give it to there. So now that manhole is 3.8 meters deep. Yes, it is deep. I mean, actually, can I just make that like 0.1? Oh, I can do that. Oh, okay, that's way easier. So some of these, like when I've used software in the past, I don't tend to use like the auto stuff. I always do everything manually. So I don't allow it to like calculate gradients and stuff for me, just because there's a tendency for like the auto design thing to like sort of do its own thing and change stuff that you're not aware of. Yeah, in this game, the auto design's like always turned on. You can't actually turn it off. So it means it will sort of change like levels of stuff that you don't want it to, because it thinks it's trying to help you, but it's not always helping. So anyway, if we change that, so that manhole is now much more sensible, 2.8 meters deep. You may be wondering, can you have like pipes coming in at different levels? Yes, that would be called a backdrop. So basically, as the water comes in, it will drop down and then it will come out the outflow pipe. Generally, you would try and keep everything sort of at the same level. I think when you're working in like sewage pipes, you can't have backdrops. But as this is only surface water, you can have backdrops, and it does make things things a little bit cheaper. Although occasionally backdrops are quite tricky to like actually build on site. So sometimes you would just like make that pipe steeper so it all comes into the same level. But for now, I think that's pretty good. So when we get to the end, the one thing we need to be careful of, can you see these pipes have been laid invert to invert? So the invert of the pipe is the bottom. The soffit is what we call the top. You can see the bottoms of the pipes, they're completely level. The tops of the pipes are not. Now this is actually really, really bad because imagine the water coming down here. Yes, it can flow straight into that pipe, but because this pipe is bigger, it's expected to take more water. But because like the top of this pipe is only at that level, this pipe will like never fill up. So it's completely pointless being that big. So what we tend to do, we make the soffit of the pipes always match up. So if you've got different size pipes from your outlet to your inlet, you'd lower your outlet pipe so that the top level is the same, because your outlet pipe should always be at least the same invert, if not lower. So in this situation, I wouldn't raise this end. I'd always lower this one. However, before we do any of that, we gotta sort out our pipe sizing first. So let's run the storm. So this is running a 1 in 50 year storm, which I think is what the game uses to calculate the pipe sizes. In real life, we'd do various different storms. We'd run a 1 in 30 year storm for the actual pipe network. To size like this pond, we'd actually do a 1 in 100 year storm for that. That's because this is quite critical. It's a massive body of water. We don't want this to ever leak. So we'd size this pond based on a storm that's meant to happen once every 1 in 100 years. Pipe networks, we'd only size that based on what would happen once every 30 years. Now you might think that's a bit backwards, because obviously if these pipes are only sized to take a 1 in 30 year storm, when a 1 in 100 year storm happens, that amount of water wouldn't actually make it to the pond, because your roads are going to flood because the water can't get through the pipes, because they're only sized for a 1 in 30 year storm. And obviously a storm that happens in a 1 in 100 year, it's going to be way worse because it only happens once every 100 years, which yes is sort of correct, but it's just more of a safety thing to make sure that this can never flood, because a pond flooding with such large volumes of water could be catastrophic. Generally a little pipe flooding isn't as bad, so you should think of it as we design our network as 1 in 30 year storm, and then we just make the pond a bit safer, rather than we design everything for a 1 in 100 year storm but then make our pipes not as safe. Also worth noting, we generally add a percentage like change. So we say whatever this works out as, we would then add a 30%, or more recently I think it's a 40%, and that's an addition we add on to count for climate change, because climate change basically it's raining more and more essentially. So all the probability models, they're all based on like previous data. I think it started in like the 1970s. So from the 1970s to sort of nowish, we have rainfall data. People have actually been measuring it. But we're slowly finding out that during that period, because it's only like 50 years or so, and we're looking at like 1 in 100 year storms, we don't know like what the actual data is. We don't know what the worst storm in 100 years is going to be. So generally we just take those graphs and extend them to think like, okay, if that's the worst in 50 years, keep the graph going. That's how much it's going to rain in 100 years. But as we're slowly finding out, we were slightly wrong, or maybe it's climate change. So we generally add whatever this says, we'd add like 40% on, just to give our networks hopefully a bit of future proofage. So anyway, our pipes are in now. You can see they're not going great. We have this situation going on, and actually that reminds me of something else. So these manholes, generally they're just held in place by their weight. There's like no handles. You need like a special tool to sort of pull them up. But I found out recently in the F1 they actually had to go around and weld these shut, because an F1 car produces so much uplift that they were actually popping the manhole covers off, like when they were doing like the road races. Now these covers are like heavy. They're like 100 kilos ish. So yeah, that's how much uplift a F1 car produces, which is crazy. It was lifting these up. But yeah, you can see this one is popping because the amount of water. Basically, we have too much water going to our pipes, so we need to make our pipes bigger. So generally, you'd probably start sort of downstream, and I don't know, if we just make a lot of these like 600s, or actually maybe from here we'll go 450. 450s. So two 450s come together and then they turn into a 600. That's generally like a rough sort of idea as to how this actually works. So as you go up these pipe sizes, like a 450 can take twice the amount of water from a 300. A 600 can take twice the amount of water from a 450. So if these two do both take a 450 pipe amount of water, then this one should work as a 600. It's a nice little sort of rough idea to like roughly do your pipe network straight away. But yeah, obviously there's several different factors. Like we have the steepness of the pipe, because if these are steeper, then more water can flow through, so they don't actually need to be as big in diameter. And also the pipe material has like different friction. So I think in here we have reinforced concrete pipe. We also have plastic pipes. Depending on which material you use, depends on like how much water can flow through, etc. Anyway, that pipe sizing seems to have worked. There's no manholes popping now, which means we can just look at the penalties we've got. So, we exceed our maximum structure depth. The limit is actually 2.7. Game lied to me. And pipes can't go deeper than 2.4 meters. So that's sort of a similar thing. Now, I imagine that's probably happened because as we put our pipe diameters in, that changed the depths of everything. So I think let's just raise some of these inverts. Okay, so I can raise this one up. So that was the pipe I raised up. So you can now see I can raise this one up quite a bit as well. So by raising that up, our penalties have nearly gone. We've just got minor and major setback to buildings. So I went too close to a building. So imagine it's that corner there. So if I just move this like that way, now our only penalty is we exceed the maximum structure depth. Now, since this pipe, I can't actually raise it, otherwise we'll be clashing with the mains. In order to get this manhole to be not as deep, what I can do, it's a bit sneaky, but looking at the contours, this flows downhill. So I can just move this like over that way a bit. So that means the manhole can be shallower, which means our penalties are now down to 0. So which means we've now completed this level. We dodged all the underground utilities. We complied with all the rules. Lovely jubbly. We spent just under 260 grand on this network. So should you check this out yourself, remember this isn't a game. It costs $150. It's not cheap, but it is the closest thing you'll get to be able to do this job in real life. Honestly, I think if you like got good at this, you could literally put it on your CV and like you really wouldn't struggle to do this as a day job. And this job is really in demand. So I would actually recommend you invest that money if you're considering like drainage as a career. But yeah, for now, I'll say peace, love. And I can't believe you guys actually watched all this video to this point. But if you did, I hope you enjoyed. Bye, guys.